அந்த இடத்துல கண்ட்ரோல் பண்ண யாரும் உள்ள சவுண்ட் கம்மியா கொடுத்துருங்க. வீடியோ ரெக்கார்ட் ஆகிட்டு இருந்துச்சு. The total specification record things Uday Kumar knows very well because I leave to him. So he explored because of him only the was here. So I could also mention this thing. He got his time for bringing this. Every time shuttling. This was our problem. One thing what we brought it from the DST part. So we need to modify it later. So our system modification. Totally we are upgrading. Basic to get system. Over the fund value. Fund value is about 50 plus. It's almost 50 point something. About a manpower salary about the capital cost is around 35 lakhs. Capital
15 lakhs, 13 lakhs.
Total. Apart from the salary, how much money we are having? 40. The distribution. We need to acknowledge the DST for providing this. And then the page on.
Yes, sir.
Very good. Ready, sir? Hello.
Yes, sir. Recording.
Let's start.
Yes.
Okay. So I am welcoming the participants for the second session, the 4 notes. That is tutorial 3. The demonstration of the equipment, what we have procured under DST scheme SERB. Now the SERB is no longer is there. It is ANS of now. So I thank the DST for providing the fund to recruit the one project associate and procuring the equipments and other expenses for meeting the demand of the world for expecting the hydrogen, green hydrogen and green ammonia. So I need Trichy, and I thank our director also providing the space for keeping all the equipments and the components present in this demonstration system. This is a non-thermal plasma generation system where the system itself we are producing hydrogen and ammonia, the single system itself. And so it is situated in thermal laboratory, and all the components we have procured and systems are working perfectly now. We are able to generate the ammonia in ppm level. The system consists of 10 kilowatt solar PV, which is there in the second floor of the mechanical faculty block, and we are delivering the power average 6 kilowatt per day out of 10 kilowatt. That is the lowest among the 10 kilowatt. And we are the power can be whenever the systems are running, power can be taken for producing the ammonia. The remaining time, the power can be given to our institute grid, and we are helping the institute also in terms of not taking the power from the grid, and we are also delivering it. So I'm thankful to DST for contribution in terms of the recent research in terms of ammonia, what we are currently doing, and also I'm giving back to my institute the green electricity. The system consists of the following components: 10 kilowatt solar PV. Each there are 19 PV cell array. Each is about 540 watts capacity, and we have commissioned that successfully. And during the commissioning, we had a lot of issue in earthing, and with the help of the faculty members and our head of the department, we have We have taken care of the earthing problem. Now the earthing is perfect, and we are delivering the power to the grid and also for some amount of the energy for running the system also. It contains solar PV conversion system, solar PV to DC-DB, then the inverter, because the solar PV will convert the solar photovoltaic, solar photons into, I can say, DC current. When we need for grid, we are supplying to all the applications in the alternative current. So we need some kind of device to convert DC to AC. We are using inverter for that. And it is going to be distributed through the grid, and some of the energy is taken for running the pyrolysis, this plasma system, non-thermal plasma generation system. So the advantage for the system is it's operated at the normal ambient temperature, pressure, and it is basically it's a cold plasma system, and it has the plasma reactor. We have the device. We have this one. Here is the plasma reactor. So our intention is to use high intensity, high voltage energy, which can be used to produce the plasma arc. So we have the provision to supply nitrogen also. So and also we are measuring the flow rate of nitrogen into the system. So the plasma, the alternative current, the energy, which can be given to the create the lightning, we call it the plasma. Nitrogen, here we have the container where the water is stored. High intensity light, plasma light is going to break the water into nitrogen and oxygen. Oxygen will be taking out nitrogen, and the nitrogen is available at the reactor. Then we are providing nitrogen also. So nitrogen, not only I can say to produce ammonia, it will also act as a plasma. I can say plasma energetic, I can say gas, plasma to create a plasma gas. And as we know that the principle is non-equilibrium conditions are maintaining. That's why the plasma at non-equilibrium state we call it the cold plasma. Cold plasma has many applications for food processing and textile and the medical as well as the electronic industries for killing the pathogens. So same kind of concept we are using here. But normally the plasma generated high temperature plasma that is used for many applications. Here we are using operating at normal temperature and pressure. That is the biggest advantage when it's compared with Haber-Bosch. So Haber-Bosch, we are operating at 350 degrees centigrade. Pressure is about 150 to 300 bar. Here the ammonia is produced at ambient conditions, and the energy needed for producing ammonia is, I can say, for splitting the water and for combining the nitrogen with nitrogen, we are taking from the solar PV. So it's a renewable based ammonia generation. We are claiming that is a green hydrogen generation also coming out. Green ammonia also we are producing, and then after producing the ammonia from the reactor, it goes to the deep freezer where we can able to go up to -40 degrees centigrade. And part of the project we procured this one also. As you all know that ammonia has a boiling point of -3.33. So if you maintain at that temperature, along with ammonia, there are few more traces of gas will come out in the form of nitrogen oxide forms, and other gases, nitrogen also will be available. That will be taking out. In order to take out the ammonia from the different constituents of gases, we are going for deep freezer to maintain -33. We will separate out the ammonia alone. Other gases will be again sent back to the reactor for the process is maintained a closed loop. So all the untreated or unconverted nitrogen and hydrogen is going back to the system for ensuring that the ammonia is coming out from the reactor. Maybe these other people are contributed for this sector. Currently, Mr. Saravanan is working on this project, and maybe they will explain how the system works.
Myself Uday Kumar, and this is Dollar Chemical and Industry. So the system is purely producing green ammonia. Here we can probably say this is green ammonia. As we discussed in lecture section also, whether it is green or blue or gray, so those debates are happened yesterday lecture. Here we can 100% confidently say this is green because we are taking power. We are not taking any power from grid. We are taking power from solar and we are utilizing that for generating ammonia, and also we are not utilizing any fossil resources for fossil resource as a hydrogen resource. We are generate hydrogen from methane, or if we generate hydrogen from coal or hydrogen from some other fossil, then we can't say 100% that is green. And also we are not taking hydrogen from plants also, biomass also. So here we are taking hydrogen from water, but it is not like electrolysis. Electrolysis process also we are taking hydrogen from water, but this is purely differ from electrolysis, as well as it purely differs from methane reforming. One major two techniques other than hydrolysis, one is electrolysis, another one is methane reforming. So both are not utilized here. This is another growing or developing method to synthesize ammonia. So here we are taking water and we are utilizing one more third factor, that is cold plasma. We all know that plasma is the fourth state of matter: solid, liquid, gas, and then fourth state is known as plasma. So that plasma also we can classify that into thermal plasma and non-thermal plasma. Thermal plasma has certain property and it has own applications. Non-thermal plasma has certain properties. How we can classifying plasma means thermal and non-thermal is based on equilibrium. If gaseous temperature is equivalent to electron temperature, then we can call that as a thermal plasma or else equilibrium plasma. So equilibrium plasma in the sense the temperature of gas is very high. It's more than 3 to 4,000 degrees centigrade. It can go up to 40,000 degrees centigrade. So depends on the application, we can create that plasma. That too based on the application. In cold plasma cases, we are not creating high temperature plasma. Here we are generating low temperature plasma. How we are generating it? We are just activating the gases, converting that into ionized form, not completely ionized. Partially ionization. Partially ionization happens due to the activation. That activation also, if you increase the current value, then we can generate thermal plasma. Generally, we can say like that. If you increase current, then we can get thermal plasma. Low voltage, high current will give thermal plasma. High voltage, low current will give cold plasma. So here we are utilizing high voltage, and we are converting that high voltage into plasma. High voltage arc is used here for creating plasma. For thermal plasma means we have to go with low voltage and high current. So here current is milliampere range, but the voltage is kilovolt range. Okay. About 20 up to 40 we can go by this setup. So this is high voltage setup. What are all the components exist with this ammonia complete synthesis unit is first source of ammonia. One is nitrogen, another one is hydrogen. Nitrogen is directly taken from pure nitrogen from nitrogen cylinder, and then water is deionized water. That also we are producing in laboratory. By taking water and producing deionized water. That deionized water is used as a hydrogen resource. And then third input is electricity. That electricity is derived from solar. So nowhere we are using carbon resources. So here electricity is taken from grid up to 230 volt only. Single phase 230 volt. Send it to a transformer is there. So that transformer is increasing the voltage and anyhow power is constant. We know the energy conservation things. Whatever we are giving in V is power. For general case, we may add a gas coil also. So V is power. The power 230 into how much amps we are taking, that is input power. That need to be equated with whether we convert that into high also, the same power only. So that much current is reduced, voltage is getting increased by the transformer. Inside inside the electrical component doing that. So that transformer, that is turbo transformer. So it is increasing the voltage up to 40 kilovolt. So here where we can start the R depends on the secondary factor, that is the distance between electrode and water. Okay, so here we are using drainage water. This is water tank. This is the reactor. Actually, you can see the rod inside. You can see the rod, that is electrode. This is rod electrode. We may use button electrode, needle electrode. We may use so many types of electrode. Depends on your needs. For our application, rod is fine. And then ground electrode also there, that is disc plate. One more electrode is mounted on the center. I think you will find the
Basement. What is the basement? Electrode material.
This is graphics.
This one. Oh.
Yeah, both are.
Bottom.
Disc electrode also.
Both are same material.
Yeah. Here we are giving high voltage. Here high voltage, bottom of the disc we connected with the low voltage. Okay, so I mean high and ground. We usually call that as ground. This is high voltage. So we are maintaining the voltage between the high voltage and ground is 20 K or 25 K. We can adjust through this now. So here we are adjusting the voltage, and based on that height difference. If the height difference is low voltage, we can generate or we can create that arc. That arc is nothing but that is cold plasma. You can visualize that. Okay, so that arc is penetrating over the water. So actually we are supplying nitrogen as a source for plasma, because the gas is converted into plasma state. So that gas is nitrogen gas, and the nitrogen gas is converted into nitrogen plasma. Nitrogen plasma in the sense ionized nitrogen. So the ionized nitrogen may contain N plus, N2 plus. So nitrogen is dissociated. Yesterday we discussed about nitrogen fixation. So nitrogen fixation is the major challenges in ammonia synthesis. For nitrogen fixation only, we are going for a higher voltage and higher temperature. As yesterday John Ku said, nitrogen fixation is one of the biggest challenges. Next one is hydrogen evolution. So hydrogen fixation is completed or achieved by through cold plasma. So it is giving it is easy in the operation, and nitrogen fixation is happened. Nitrogen fixation is nitrogen N2 is broken into N plus ions. Not N2 is converted into N. That N also unstable, but here it is not coming as N plus or N2 plus will come. Sometimes N2 also remains in same. So that N plus is highly reactive. It can easily react with hydrogen. We may give hydrogen also as a source. Second thing, we can give hydrogen also as a source, but for hydrogen evaluation also critical issue. So here we are directly using water, so that it needs extra fixation. So that secondary thing for splitting the water into OH minus and H plus or H2O2, some unstable forms. That form is done by through UV rays. So secondary thing is UV light. So that UV light is also one of the actuator, or we may call that as a promoter to enhance the reaction. So first thing is we are using plasma as a primary enhancer, a primary factor. The secondary factor what we are using here is UV lights. The UV light also we are using different wave numbers. So different wavelength we may use. Different have different input or different output we receive. So that UV light helps to enhance the hydrogen evolution. So that hydrogen evolution and hydrogen fixation both are done with two technologies. So everywhere electricity is input. So here we are converting that into then the reaction will happen. Hydrogen fixed and then H plus also evaluated. So N plus H will react and form NH3. So that NH3, along with NH3, so many additional products also or unwanted products also forming. So that unwanted in the sense that also ionized form of gases. So that is highly reactive, that is highly useful. We need not to lose that converted or ionized thing. So that we are separating ammonia alone, and then we are taking remaining gases and send back to the system. So that is already reactive. So again, it easily deform and usually NH plus will form. Then second case NH2 plus and NH2 plus, like it will form so many radicals. So our precursors, radicals, we may call that as a precursor or radicals. That radicals easily form ammonia. Once we feedbacking that, or we are continuously running more than 15 to 20 minutes, then the production rate will increase. So here we can segregate the ammonia. This is called a deep freezer. Here we are utilizing using the principle. Here we are using the principle of cryogenic technology. By there is a different condensation point. Ammonia condensation point is different, and then H plus N2, H2 condensation points, everything is different. So the different condensation temperature taken as a principle, and particularly we are maintaining the temperature for ammonia condensation. So from 30 to 40 other elements own condensate. All other gases are taking more than 170 minus 170 degrees centigrade for condensation. So that is achieved by that difference is very much useful to us. So we are maintaining 30 to 40 here. So that temperature condensate only ammonia. Remaining gases will remaining thing will come as a gas. That gas is sent back to the reactor. So this is the actual thing. Here we have coils.
Camera.
This is a decreasing chamber. It will go up to minus 40. So here we have actually this is the reactant gas. After the reactor, the gas is coming in. So here it is coming in and then sending through the coil. And after circulating through the coil, it is sent to this is collection chamber. It will collect the liquefied ammonia. Then remaining gases alone taking out and sending back to the the simple freezing chamber modified for our application. This is actually freezing chamber, or we may call that as a cold chamber. The cold chamber is modified based on our application. For reaching 40, it takes 45 minutes. From room temperature to minus 40, it will take 45 minutes. The number of turns in the coil is reduce the time for condensation. Yeah, actually that we can do that. If you reduce the turns means we can't exactly predict how much ammonia is coming. Sometimes we can't predict that reaction because actually that ppm is ranging from 70, 80 ppm to 1000, 1500 ppm possible. So we can't tell constantly, continuously we get the same output. So the heat transfer thing is secondary phenomena. We may give some other shape, or we may enhance the numbers, or we may reduce the diameter. That is secondary research. So actually, the purpose of this is to condensate. Actually, our concept or our focus is initially we started and we developed the system based on the generation. So our ultimate intention is to increase the production rate, increase the PP. So the second thing is that we may modify. Generally, we buy and we design the coil. That coil we modify. This is separate result. This is heat transfer result. So here we are concentrating on electrochemical part. And then we can take liquid ammonia out, and we may store it in one thing is we have to store at low temperature, or else you have to store at high pressure. So both are possible. Pressurizing is for small scale is difficult. We we discussed about that also. After discussing with professor and after discussing with the expert member, we arrived rising the pressure is for small scale is difficult. Rising pressure for large scale may be possible, and also ammonia is highly corrosive. So we can't use conventional compressor for this. So we derived and we tried with low, and then afterwards we came to conclusion that cryogenic point is condensation by means of temperature is easy compared to by means of pressure. If you raise pressure from atmosphere to 11 Fahrenheit, automatically condensate. Others atmospheric temperature 30 degree or 25 degree to minus 30 degree, then it will condensate. For maintaining temperature is easy. For compressing that here flow rate is low. For this is for lab scale thing. If you scale up this, then we may try with cryogenic as well as we may try with the compressor. Then we may compare the energy efficiency.
Here our aim is to produce ammonia. How to store the ammonia and within the research perspective, we are finding another method to store the ammonia. But later this may be extended in terms of energy perspective, in terms of economics perspective, in terms of environmental perspective. We are currently thinking about LCA, life cycle analysis, which method can be compared with the commercially available method of producing ammonia. When it's compared with our work and bringing what is available with us, we do the comparison. And where we need to pinch it and so that the further reduction cost can be reduced, that is the further research. So we are success in producing ammonia, what people are using by using electrolysis, then highly energy intensive process. We have produced ammonia through green route from solar photovoltaics.
Is it applicable to the power input or the output is more or less this matching of other than the
Actually, the power requirement for the running this is low, very low, because it's less than kilowatt. Actually, power consumption is low because we are using 230 volt normal 16 amps which only we are using. So very low power only it's consuming. And compared to that, it will give great yield. For this setup point of view, energy is efficient as of now. And then secondary, segregation of ammonia from the mixer, that is secondary thing. For these, we are consuming energy. We all know that refrigeration or energy. Yeah, main part. This is it consumes less than 1 kilowatt. Actually, we installed a 10 kilowatt, but for this 2 kilowatt is maximum. Includes now the control unit. This control unit it automatically detects the pressure, flow rate, nitrogen flow, nitrogen pressure, and then third factor is gap between water and electrode. So that is all we are monitoring online, and then this will detect the conversion person. It will calculate the ammonia yield, how much the gas is converted into ammonia, that we can calculate it.
the gas meter or something.
Yeah, it's a sensor, ammonia sensor. So it will detect the ammonia, how much ammonia is coming out from the
By volume.
yeah, it is giving ppm, sir. We can convert that into ppm into all.
Conversion.
Yes.
1 unit of electricity, how much ammonia is coming?
You saw that.
So we are supplying nitrogen and
Gases. Liquid state it will supply water. Liquid nitrogen is very difficult actually. You have to compress it 200. Yeah. We are sampling in gas. Compressed nitrogen, what we obtained from market. Gas separation unit is there actually, that is separate research. From atmospheric air we can bring nitrogen alone. The gas separation that also done by cryogenic. By the temperature difference only they are extracting nitrogen from atmospheric air, and that is they provided. We are getting cylinder only. Air water only in laboratory we are making.
can use recycle the same ammonia for
Same ammonia for
nitrogen.
why it is? I want ammonia, then why I have to recycle that into nitrogen? Actually, I'm not wasting any radicals. I'm not wasting any precursors. I'm recirculating that into reactor. Yeah.
That nitrogen can be used.
No, that actually mass in equal to mass out. So you have to give, you have to simply circulate. It means I need a source. One so hydrogen source is water, nitrogen source is nitrogen. So I have to give something. Then only I can get. Nothing is created inside. We are supplying electricity, energy conservation principle. Another one is mass conservation. We are giving mass.
See, you need some amount of nitrogen, even then you are recirculating again and again. Something is already consumed for converting into ammonia. Suppose you are taking some food, right? Some quantity of food. Something is taken for remaining is there, but that is not your actual food. So you need some minimum, some quantity of food, right? Similarly, the in is fixed. How much the nitrogen has to pass, how much the water needs to maintain is fixed. So when the conversion happens, how much the loss of nitrogen, maybe unless one you can circulate it. But out of that, some needs to be supplied to maintain the mass balance. Right? Okay, now request to Saravanan to explain how you are carrying out the experiments.
So I'm Musa professor and explain all those things. So here there are four main components. We are one is the solar power, and second one is this MTP generator, and third thing we are having control. So that will be display all the readings that are how much input we are giving, mode of voltage, current, and how much pressure is given, and flow rate is flowing through the reactor and all can be controlled and can be monitored. And we are taking the readings. And second thing is here we can control all the things here also manually, and everything will be data logged to the control unit. It's a PLC unit, so that will be giving over the HMI also. So there we can take the reading. So here we are getting the power from solar. So that power will be given to the grid, and we are getting it directly from just operating this equipment. So here we are giving the source of ammonia as I told you. Nitrogen is there. So here we are buying it from outside, but we are trying to make on our own by separating from atmosphere. And for the source of water also, we are doing the distillation process here, and we are getting the water source. Yeah, and here the main thing is we are doing the plasma water interface actually. When we are interfacing the plasma with water, that will give the output of the product, that is ammonia. So here nitrogen will be passing through the reactor. So that what will happen here, water already inside, and we are sending that electricity between the electrode. That resistance will give the plasma of the gas actually. Whenever we are actually plasma will be generated as well by heating or electricity. So when we are sending the electricity through the gas, the molecules will be broken into many parts as the radicals or ions like that. So when we are giving the electricity to the gas, the electrons will be going out. As it is having very less mass content, it will take up most of the energy. So that will free around. So that what will happen, the temperature or the energy of the electron will be higher than the gas or ion or free radicals. So that is what that non-equilibrium, non-thermal, we can say non-thermal or cold plasma, low temperature plasma. So here, that dissociation of the gas is not only affecting the nitrogen, that also help the water to get dissociated. Hydrogen molecule, oxygen, everything, H plus or OH minus like that. So when that nitrogen will be mixed with that, will be producing the ammonia. And unfortunately, not only direct ammonia will be produced, along with that, free radicals will be formed. N plus N plus N2 plus like that, and H plus NH plus also will be coming, and the O2 molecules also break down. So every radicals will be flowing through it. And that will be that ammonia will be stored here, converting into liquid form, and that other unreacted reactants will be recycled with the along with the nitrogen supply. What we are supplying through the nitrogen, that will be so it will be enhance the ammonia rate actually. We are increasing the flow rate of nitrogen along with the free radicals. Already it is decomposed, so it can be easily mingled with the water particles as well as nitrogen available, so that it will be increasing the rate. And the second, we are till now we are working on the inclusion of the production radius. One is this way. Second one is UV, ultraviolet rays. So it will enhance the dissociation of water particles. When we are supplying the UV light over the water particles, it will be easily dissociated. So that the H plus ion required for this ammonia production will be easy for us. So that things we are doing. And here we are using the electrode. So one is a high voltage electrode, another one is ground electrode. Between that, depending upon the gap between the water and the electrode, the plasma will be made. And plasma properties, the density and that stable time duration and all will be affect the ammonia production. So what will happen now here, the plasma will be generated until the power we are given. So here we are running the equipment with respect to 5 minutes, 10 minutes, 30 minutes like that. So until that, the plasma will be continuously generated. With respect to the time, ammonia, nitrogen flow rate, as well as that gap between, especially here we are having that gap adjustment mechanism in the top electrode. So here we are having one needle electrode and display electrode. So between that voltage current will be passed so that plasma will be generated in presence of water. So here are these things, and here we are having PLC net, and we are controlling all the things that before sending to this equipment, we are checking that what is the pressure, what is the flow, so that we can supply it. Okay, and then next we are all having lot of advanced technologies here, as we are having this LTP generation.
Start the process. Yeah.
Yes.
How will you fix that voltage? How much voltage we require based on the thing?
Can we finish it up?
Depends on the gap. By adjusting that, we can isolate.
Now Mr. Saravanan will give the demo of how the ammonia generated in the plasma, non-thermal plasma reactor. I think the participants can visualize that process. And if you will have any questions, maybe at the end of this one demo, we can post them. Most welcome.
So here I am giving the
So, Mr. Saravanan is now controlling the flow rate of nitrogen from the cylinder. Which you can see here, the nitrogen flow is happening, and you can be able to measure the flow rate also through the nitrogen flow meter.
so here.
Don't come very near to that.
I mean, high voltage, don't come very.
Effective measures to be taken.
If you are on the high voltage will be applied here. The caution will be taken here. Non that's that. From here, I have started the nitrogen supply. So here we need to get the water supply. So that will be getting from the
Water tank, enter into the air.
the distance is very high, the plasma intensity will be very low. It will be very weak. So here I have given the water supply, and we can also here adjust the gas flow, or how much LPU of nitrogen need to be given and everything. And if you have that things here, so here I am giving a high voltage. So here we are having a HMI. This will be displaying the high voltage.
And
here I'm going to start. So here I can see the frequency, voltage different, power and current and all. So here. So whenever I'm giving this actually high voltage on, I can be ready to supply the power. So here the voltage node can be used for adjusting the voltage. So here again this the voltage is actually that the current also will be ready. And you can see there the plasma generation between the electrodes. As I have given that is we can so when we are giving maximum distance, the plasma intensity will be very low, and when we are giving high, then we have the possibility of attraction of the molecules to the electrode. So that so I think
Let's ask that.
yes,
Thereafter, no formation.
no formation. So it will be attracted to the and it will not be stable also. Plasma will not be stable. But then there, the flow of nitrogen will be there.
I will get what level is there.
It can be 40, but we don't want it. It's a maximum, but we are giving 40, 21, 20 kilo oxide, 20 kilo. The maximum is probably will be and here, and here when we are giving exercise. Exercise.
Yeah.
Yeah.
First, தண்ணி மேல போயிருக்கு.
The different condense is water actually. After attracting, they made the payment. But the public. If they know that the distance between the water and the electric is not exceeds 7 inches. If we know that now that the power cannot be produced, the gap is very big, so that the. So we that track and actually, but first we have when we do borders, that track, so it's landing, if we want to keep the electron electricity now, so that will be divided by the water content attached to that. So we need.
ஃபீல்டு பார்க்கலாம் டிஸ்பிளே பார்க்கலாம் கரெக்டாக penetrated plasma properly penetrated over the water, then it can continuously produce ammonia. Initially, 2 to 3 minutes, the ppm will be low. So after 5, 6, 7, continuously ppm level will increase. Anyway, we are not modifying nitrogen flow and then water level. We are freezing all the other parameters. We just operating after certain period we will maintain. So it will give the after 30 to 32 minutes, it will give the.
And then you can automatically input the water. Not like
Yeah, we need not to add water continuously. The water will consume very less quantity. Compared to, yeah, consumption, it will be very low. To run more than 3-4 hours, no, then it will. Actually, it needs some cycling cap. 45 minutes, no, then we have to give at least 15 to 20 minutes. Yeah, continuous running. And then that is stored the water. Here we are storing. The electrode and then pure electrode nowadays that cap, like not use black, not use silver. That acts only reflecting. And some water will look like yellow is
because I don't need like hydrogen for electrode. Same that exceeds for the but same level is.
yeah, the water will gets converted over. Some of ammonia may dissolve in water. After some time will come. After stopping the reactor, it will come. Other will come out. Don't stay being property. After some time it will. அது வைக்கிறீங்க அந்த இடத்துல வாட்டர் மெயின்டைன் பண்ணுறது மவுண்ட் பண்ணாம இந்த சைடை வச்சுட்டு actually oxygen is right now we are not taking any oxygen out. It also dissolve in water. So it adds to the temperature. It dissolves again in water. It adds to the plasma. Actually here it is cooling. Cooling happened. The outlet gas temperature is minus 30 to 40. Okay, here minus 30. That will display only. They're monitoring the voltage and the current. You can vary voltage alone. You can't vary the current default. With respect to our input, so that is, and then with respect that you can use the our supply is constant. Here we are varying. So depends on that. So, you know, we are not taking adding water at the time of running. It also contact. Oh yeah, that water will contact. High voltage, that's why you have. Actual gate, you can't run very close at it. Inside the box, you will answer that. You completely close, but it will be. I need not to open. I can see the current it comes black might indicated now. I need not to open it. I can see the display. Current value. We go up and one black might indicated now. Current will go down. Easy. You see the video. You do the other black might indicated. Game on. After the plasma initiation, we calculate the time. So based on the time, we can get the different output from our paper. We get the law. Yeah, it will have that. Actually, the power is more in currently. The current is more than compound, and if the transformer, automatically will cut off. So I need to maintain that answer.
Now it's control of the
Yeah. Actually, that current value getting increased, that also problem. It will go up to 7.5 million. In that way only we have to run the during no rates come out. It's safe to operate. Here different wave numbers are there. Two lamps are fixed. If I turn on these two, that wave number and next wave number. So designed with three different wave numbers. So it also give small impact for the production. Without UV, the production will be low. So I can roughly say it will increase 10 to 12% of it by UV. For UV also simple UV lamp only. Right now we are using simple UV lamp only. We can modify the wave number. We are getting standard standard lamps only for UV. That also not the actuator promoter. Here we may detect, we may find the yield, how much ppm is generated. So this sensor, this will give the yield, how much ppm is coming. So based on that, I can calculate the yield in terms of mass. So what I am giving, what I am. So here we are purely dealing with the energy with the yield. So how much energy is input, how much is yield.
Yeah, this is the made in India concept. So as per our design and we approach the manufacturer and we have come up with the in-house design and we are successful in getting the ammonia. I hope probably this may be upgraded for increasing the yield by bringing some of the concept into the system. Maybe in the coming years, the ventilation may be percentage of yield as well as the drop in maybe the power input to the system also maybe enhance the method. Thank you so much.